Welcome to yet another video on Financial Math for Actuarial Exam 2. This is video number 174. In this video we are extending exercise 7.2.3 from Broverman. We looked at that exercise and solved it in the last video. It was kind of a theoretical exercise that connected immunization, Redington immunization, in terms of derivatives of present value functions to certain summations. We'll look at the statement of that problem in a minute here. We are extending that problem in this video. I also want to say that this video is connected to the content of a couple other videos, which I'm going to put links to all three of these videos in the upper right corner here as we go. It's also connected to videos 171 and 172. You can see we're going to use a spreadsheet here instead of Mathematica. The numbers involved in the spreadsheet, which are asset and liability cash flows and certain interest rate, they come from video 171 and 172. I also did refer to them in video 173 as well. Okay, you know that often I use Mathematica, but most people don't know Mathematica. More people know spreadsheets, so I want to give some content where people can get some benefit out of using spreadsheets, and I think the content of exercise 7.2.3 from that last video is especially nice to emphasize that you can use spreadsheets for that. Alright, let's look at the problem statement. Here is the problem statement for exercise 7.2.3. Actually, in Broverman you only find this far, and then I added a part C. I modified it in the last video. The context is the same as what we've been doing recently. We've got asset and liability cash flows. We've got these present value functions for the asset and liability cash flows. I is an arbitrary interest rate, arbitrary periodic interest rate. V sub I is your arbitrary periodic discount factor. It equals 1 plus I to the negative 1 power. In the context of the entire problem, we assume that we have matched present values. At some specific interest rate, I0, we have matched these summations and these function values. Okay, that's a background assumption. Part A says to show that this condition, that the derivatives of these present value functions at I0 being equal is equivalent, means the same thing as these summations being equal, which is not completely obvious at first because when you take the derivative you don't actually get those exact summations that you see there, but something slightly different. Okay? Part B of the problem says that if you, in addition to assuming that you have matched present values, also assume that you have matched durations by assuming that these derivatives are equal, then you get three things that are all equivalent. The first thing being that if you assume that the condition that the second derivative of the present value function satisfy this inequality, that the second derivative of the asset function at I0 is greater than the second derivative of the liability function at I0. That condition is equivalent to this one, which is also, you can see, a greater than, but now with summations. And that's also equivalent to this condition, which is also, again, a greater than with summations. Do notice the similarities and differences between these things. With present values, you don't have extra factors of t or t squared in there. With durations, thinking about the derivatives, you do get these extra factors of t in there. With now thinking about second derivatives, you get extra factors of t squared, both here and, well, t minus a quantity squared here and here. It is emphasized in Broverman's book that di represents either Macaulay or modified duration, though I did emphasize in video 173 that actually that's a little bit misleading. Di can actually be any quantity that is independent of t, that only depends on I. It's going to be most useful to us, we will see, to think of it in terms of Macaulay duration. That's what we're going to do in this video. That'll be the most useful perspective because we can make some connections with probability and statistics, actually. Means and variances of discrete random variables. That'll be a subject to some future videos here. We'll also refer to part C in the spreadsheet, in the second sheet of the spreadsheet, from a couple videos ago, video 172. Well, quick summary of what happens in video 171 and 172. We are solving an SOA sample exam problem from October 2018 in video 171. And in that problem we see that we're actually not immunized. Okay? We do match present values and durations, but the second derivative condition for Redington immunization is not satisfied. It's not a greater than, it's a less than instead. And then in video 172 we tried to fix that by changing the moment in time of the second asset cash flow and it turned out to occur at a strange time, 3.57207 was the time of the second cash flow, to just be at the boundary between not being Redington immunized and being Redington immunized, where the second derivative equals 0. So you're passing through it being negative in a graph that's concave down to being positive in a graph that's concave up. That will come up in the second sheet of the spreadsheet. Let's go back now to the spreadsheet and do the content of this video. Another thing I'm trying to get across in this video is the basics of how to use a spreadsheet. Probably most of you know how to use a spreadsheet already, though maybe some of the things I'll do will remind you of maybe some things you've forgotten. If this is new to you and you've always just used calculators and have thought about all these theoretical questions and haven't used a spreadsheet, then you're going to learn something new. So I've got it up here. I've got, again, two sheets here. Video 171 is what this is labeled, and videos 172 and 173 is what this one is labeled. These ones have numbers all filled in. This one doesn't, because I want to actually fill in the numbers for you. In all the videos, the interest rate is 10%, 0.1. That's I sub 0. And the first thing I want to do is figure out V. V sub I sub 0. I'm using that notation right here, though I don't use it here, 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 and here. Don't worry about that. And I want to program it in a spreadsheet with a formula. Why? Because formulas have a nice benefits. They allow you to do some nice copying and pasting. They also allow you to modify things. For example, if I want to change the interest rate, I can just change it in the one spot in cell B6, and everything else might get updated correctly. Now, it also might not get updated correctly. You have to make sure you program it all correctly, but that's a nice feature of spreadsheets, is if you use formulas correctly, it definitely saves a lot of time. Alright, so what do I want to do here? I want to use the fact that V is 1 plus I to the negative 1 power. In other words, it's 1 divided by 1 plus I. Typing the equal sign, like you see here, is the signifier to the spreadsheet that a formula is going to be used. So you can see I typed equals 1 divided by, in parentheses, 1 plus B6. B6 is where I is. It's in cell B6, and you can see it got highlighted there as I typed the B6. Now when I enter this, this will calculate B. 0.90 repeating. Okay? And because I've calculated it as a formula with a cell reference, B6, I could, in theory, change B6, for example, to 0.2 or something, and then the number in cell B7 gets updated automatically. Okay? There's a nice feature of spreadsheets. I can make changes and affect other things. Let's go back, though, to our original numbers. I0 is 0.1, and then the corresponding V is 0.90 repeating. What do I want to do? What's my goal here? My goal is to confirm from video number 171 that we are not Redington immunized. Not Redington immunized, but we do match present values and durations. Coming back to the context of this problem from Broverman, this equality is going to be true, and this equality is going to be true because we're matching present values and durations. But this inequality actually is going to be the opposite direction. It'll be a less than, and that's going to mean this is going to be a less than, and this is going to be a less than as well. You might say the opposite condition of these things is less than or equal to, but don't worry about it. We are going to get strict less thans. This does involve the numbers from video 171. We've got a liability cash flow of 500 at time 1 and 1,000 at time 4. And then in video 171, we solved for the asset cash flows that we needed at time 0 and time 3 to match present values and durations. But we will see we're not immunized against changes, small changes in the interest rate. With small changes in the interest rate, we will be put in a deficit position of the assets with respect to the liabilities, which is not a good thing. You want to be immunized. So let's see how this works out. So again, I'm going to program the spreadsheet. I want to fill in the table that you see here with numbers that come from formulas. You can see in the notation of the columns here, I want to compute the things that you see here. So in this first column here, column C, I want to compute AT times V to the T for each one of these ATs. Now, some of them are zeros, so we'll get zeros here, but that's okay. I want to do it with a spreadsheet formula. So I could type equals V10, that's where AT is, times v to the t. Now I could type equals b10 times b7 raised to the a10 power. However, if I copy and paste that formula downward, which is what you want to do with spreadsheets, that will not get copied and pasted correctly because all those rows, the 10 and the 7, will get updated to 11s and 8s, and then 12s and 9s, and then 13s and 10s. That's the way spreadsheets are set up, and that's a good thing in general. But we don't want the number V from cell B7 to get updated. We want it to stay in cell B7. So you have to use dollar signs to do that. The dollar sign doesn't mean money here. The first dollar sign in front of the B there will fix the column. That's not actually necessary to use here. We need to fix the 7. The second dollar sign in front of the 7 will fix the row. I, in general, like playing it safe and not worrying about it and using both dollar signs. Technically, only the second one is necessary here. But that will definitely fix the number that's from cell B7 as I copy and paste downward. I do not want dollar signs for the B10 or the A10. Notice I just raised that to the A10 power because I want those to get updated to a B11 and an A11 and then a B12 and an A12 and then a B13 and then an A13 and a B14 and an A14. I want those to get updated. Okay, I can just copy and paste this downward or click and drag the lower right corner here. And you could double check with your calculator. 1062.19976 is what you get when you take 1413.78788 and multiply it times V to the third power, 0.90 repeating to the third power. You can double check that you get that. All right, the present value of that asset cash flow can then be found by adding these things up. I'm about to compute the summation that you see right here. Okay, the present value, also I could think of it this way too, when I equals I0, which is 0.1. That can be done with a formula as well and use a built-in function, equals SUM for sum. And then I can just highlight all these numbers, or I could have typed in C10 through C14, highlight all those numbers, those will add them up, and you can maybe double check it in your head. You'll get 1100 something. Yep, 1137.56 approximately. Okay, I'm using more decimal places here than comes up in the videos, I think, because I want to get as much accuracy as I can. But in general, you'd want to round these to the nearest cent. All right, so that's the present values of the assets. What about the liabilities? Actually, I can copy and paste what I have, well, here downward as well, almost. If I do that, it won't be quite right because the, no, actually that will be, excuse me, that will be right. Okay, I can copy and paste this downward because the B7 already had dollar signs, and that's what will happen if I copy and paste it downward. It'll stay with dollar signs. And these are the correct numbers here. You should double check that 500 times 0.90 repeating to the first power is this, for example. Then I can add those up with the sum, and I can copy and paste this formula downward into cell C26. And I remember I matched present values. I should get the same sum, and I do, okay? Even to that many decimal places. So we have matched present values. These two things are equal. Did we match durations? So we've confirmed the equality here. Now let's see that we have matched durations. Let's confirm this equality right there. So I go back to the spreadsheet. I want to compute these products and then add them up, and I should get the same thing for both the assets and the liabilities. Similar kind of formula that I can use. I need an extra T in there initially from cell A10 that I do want to get updated to A11 and an A12 and an A13 times AT times V to the T, V again being from cell B7 that I want to stay fixed. I use dollar signs raised to the A10 power. 0 here for this one because T is 0. Okay, that happened. That's what happens in that case. Copy and paste, click this, drag downward, copy and paste the summation over. There is the summation of these numbers. If I do it over here, I should get the same answers, and again I can copy and paste. I could copy and paste this whole thing here actually, including the summation. And lo and behold, look, I get the same answer to that many decimal places even. Okay? That does match durations. Now I haven't actually calculated the duration. I can calculate the Macaulay duration from this because what it really is it's really this summation divided by this summation. Okay? If you go back to the definition of Macaulay duration as a weighted average of times of payments, in the end it ends up being the sum of these things divided by the sum of these things. This divided by this. That's going to be the Macaulay duration, and in both cases you're going to get the same thing because you're dividing the same things. Macaulay duration is about 2.80126. Okay? Average time of payment weighted by the present values of the payments with respect to the entire present value of everything. So we again have matched present values and durations. Alright, but again we said we are not Redington immunized. So even though we verified that this is equal to this and this is equal to this, we will see that with these inequalities, the inequality goes the opposite direction, or less than. The asset summations are less than the liability summations. The number we get here and here should be less than the corresponding numbers that we get here and here. Let's see if that happens. So we again continue to program the spreadsheet, again this time with a t squared there. Then times AT times v to the t, b7, use dollar signs to the t power. Double check that looks good. Click and drag, summation, get that. If I do the same thing down here, I should get a bigger number. This number here should be less than the number that goes down here because again we're not immunized. So copy and paste this, we should get a bigger answer down here, and we do, yes. 9,559.8 is less than 11,382.8. So we have verified that we actually have a less than here instead of a greater than. Let's confirm we have a less than here instead of a greater than. Notice we want to subtract the Macaulay duration from t before we square. And a little tricky here, that Macaulay duration is in cell D17, and I want that to stay constant as I copy and paste downward. Use dollar signs there. Times AT, times v to the t. There we go, look that over, that should look good. Once again, the number that comes from the assets should be smaller than the one that comes from the liabilities when we add them. Copy and paste this down. Add. And then copy and paste the whole thing down here. And yes, we have a less than. This 633.3 is less than 24.56. 2456.3. We have a less than here instead of a greater than. Okay? So we are not immunized. Not Redington immunized. All right, a little bit more to go. I want to show you the results of the numbers from videos 172 and 173. I won't bother programming the spreadsheet anymore. I've got all the numbers in here, but let's just look them over. Make this a bit bigger here. So what happened here? The key difference is that we were trying to Redington immunize ourselves, and in particular try to find a time of payment for the second asset cash flow that led to at least the boundary of Redington immunization, the boundary of the second derivative changing from negative to positive, the graph of the h of I function, if you remember that, changing from concave down to concave up. It's hard to do that, concave down to concave up like that. And what we found was that the time of payment needs to be about 3.57207 to be at the boundary. And what we see here is that does happen. Essentially what we get here is equality of present values, equality of durations, Macaulay durations that come from this fact, and we actually get equality here up to some slight rounding error of this thing and this thing. So we're right at the boundary of being Redington immunized. These two numbers here and here match. And notice those are the same as the present values in the previous one, here and here, which should make sense. I mean, the liability cash flows are still the same. the durations are still the same. 2.80 comes from these two numbers here and here matching still. These numbers were different, by the way. The asset cash flows do need to be a little different than they were before here because they need to be adjusted by the fact that this one occurs now at a different time. But now we get this number matching this number up to a small amount of rounding error, and this number matching this number up to a small amount of rounding error. Okay, so we are again essentially at the boundary of being Redington immunized here. And so I hope this confirmed the content that you've been watching recently if you've been keeping up with these from videos 171, 172, and 173. Thanks for watching.